Hello guys, welcome back. So today's topic is going to be, this is topic 11 and it's basically experimental design and laboratory techniques. So I'm going to split this topic up into two parts where we first cover, so this video is going to be focusing on uh, how to design experiment, how to propagate error, that sort of thing. And the second part will focus on analytical techniques with respect to spectroscopic tools. So without further ado, let's get into it. So when we have a controlled experiment, we a controlled experiment is officially formally defined as an experiment which only involves the manipulation of one independent variable and how it affects one dependent variable, and every other variable is controlled. Um, so the independent variable is the variable that is experimental, that is changed purposefully. So the independent variable is the thing you manipulate, and the dependent variable is the thing you see how manipulating the independent variable affects the um, results of the dependent variable. So independent is something you manipulate, and then the dependent is this thing you watch as you make the manipulations. So, for example, if we were to design, so when we design research questions, we generally tend to go, how does independent variable affect dependent variable? And then more specifically, we could say something like, how does the percent humidity in the air affect the speed at which iron rusts? Where the independent variable is the humidity of the air, the dependent variable is the speed at which iron rusts, and you have to measure. You have to have a way to measure the d dependent variable. So in this case, they're using milligrams a day. You could use molar per unit time, and so on and so forth. So the control variables are the purity, smoothness of the surface, size, shape, and surface area of the samples, the composition of oxygen in the air, and the protocol by which the measurements are made. Those are some control variables. Nextly, we go on to processing your results and how you're expected to present them. Well, not just for the IB, but more generally in terms of in a scientific report. How are you expected to communicate your findings? So, for data tables, the first column of the table should be the independent variable. The second column of the table and any columns thereafter are the dependent variable. The units should either be presented clearly in the columns themselves, so like where you input the data, or the headings of the table. And measurement uncertainties should generally be shown in the body of the table. So the most common expected format for units and headings and in graph axis is in this format below. So when you label your axes on your graphs and headings, you generally go name variable / the unit you're measuring it in. So for example, time in seconds, molarity in molar, or that's also if you want to use the proper proper SI units. It The reason we do it this way is because it just reduces repetitive typing. Um, and then so that's how you present your data in data tables. And then for graphs, we want the independent variable on the x-axis dependent on the y-axis. Your axes must be labeled. You must have units on your graph. You title your graphs usually in the form y variable versus x variable. Spacing and placement of scale divisions should be chosen to make your data clear, but without too much visual clutter. Data points must be clearly visible on the graph, but not too large. You are not Do not connect the dots. You what you should do is use a mathematically calculated line of best fit, so a trend line shown. And if you need to know how to use a trend line, how to make a trend line in Excel, I'm sure there's other videos on it. And then error bars should be shown in your graphs. If you're using Excel or whatever, data points and lines should not have shadows, so try and keep the bar graph simple and uncluttered. Size your graph such that it's easy to see, but don't manipulate don't exaggerate the scale to, be honest with your data and reflect that in the size of your graphs and so on. Um, and then lastly, you only need a legend if more than one line is plotted on the same graph. So a line of best fit is a line that is a line of best fit is a theoretically calculated line that best fits experimental data that you've plotted. So best fit lines can either be chosen to be linear or curved. And the way we can measure the how strongly the line of best fit correlates between the x and the y variables is by using a value known as r squared, the Pearson squared correlation coefficient test. Basically, the closer it is to 1, the more your data is correlated with each other. And typically, we would consider something significant if it's an r squared value of 0.8 or higher. Generally is when we would start considering, okay, these things are clearly related by some degree. It obviously depends on the specific tolerances of your course and so on, but generally speaking, the closer it is your data is to 1, the closer your r squared value is to 1, the more correlated the two variables are. And then you can use other statistical tests such as ANOVA or t-test or whatever to determine the association between the two variables, like if one causes the other and so on. But that's a topic for a different video. So here's sort of an example of, proper sort of presentation. So here we have a data table, volume versus mass, and then here we have mass versus volume of copper on a graph, and we can see here that the line of best fit, it goes through each error bar or each point, and you can see here that about half your lines are above the data point and half of them are below. Half your data points are above the best fit line and half of them are below. Generally, that's what you should be aiming for if you're doing these by hand. We can see here the uncertainty listed here. However, you can also list your uncertainties in the headings, such that you can also list your uncertainty in the heading if it's all the same. It just, again, helps reduce clutter. That's another acceptable way I've seen it. And when you do graph it, you can have a couple types of relationships. You can have a proportional relationship, a linear relationship, an inverse relationship, or a square relationship, and so on and so forth. You can either have it in the form of y equals mx, mx plus c, m over x. It doesn't really matter. And you generally use software. Excel can do this. I've used Logger Pro, which is another piece of software that is more specifically designed for science. So you can use all sorts of programs to do it for you. And I might do a future video if I can find some experimental data in terms of how to process your data, and so on and so forth. RMSE, I've already talked about. Root mean square error. Oh yeah, that's another thing I should talk about. Root mean square error. It's essentially the average error in your experimental y values in relation to the theoretically calculated best fit y values. Basically, it's a measure of how close your line of best fit is to the line of best fit is to matching the data points. Alright, so now that we've covered sort of some basic experimental design and how you present your results, how do you process your results? Like, how do you get from raw data to process data? Because while I've certainly shown you how you present your process data to in a scientific report, how do you process it? Well, we have these things called error calculations, and the first thing we want to talk about is absolute and relative uncertainties. When a measurement is recorded, we can either have absolute uncertainty, which is or a relative uncertainty, which a relative uncertainty is just the absolute uncertainty divided by the measurement times 100 for a percent, and the absolute uncertainty is just the percent over 100 times the measurement. Really doesn't. So those are some important sort of formulas to know. So for example, so absolute uncertainties have the same unit as the thing, as the measurement itself. The uncertainty has the same unit as the measurement, whereas relative uncertainty does not. It's relative, like it's plus or minus 3% versus it's plus or minus 0.3 meters, or so on and so forth. So here you could express it as 3 meters plus or minus 3.3%, or 3 meters plus or minus 0.1 meter. When you have calculated results, you're expected to present your errors with absolute uncertainties in all data tables and graphs that show process data. So yeah, now what if you have to perform some calculations to your raw data to get process data? Well, this is where error propagation comes in. So this is pretty simple. So if you're adding and subtracting two measurements, you add up their absolute uncertainties. If you multiply or divide two numbers, you add their relative uncertainties, and if you raise it to an exponent, you multiply the relative uncertainty by the exponent. Those are the sort of three main rules. Lastly, if you have multi-step calculations, you have to propagate at each step. So here we have Q equals MC delta T calculation. So here we have 35.5 kilojoules, and then the subtraction, you perform the subtraction first by PEMDAS, but note that you added the uncertainties because you have to do it one step at a time, and then we converted to relative uncertainties, and then we added the relative uncertainties, and then we converted our relative uncertainty to an absolute uncertainty. And note that if you get something like this, you must round this up to match the number of sig figs that you calculated here. So although here we get 354 kilojoules, we can see here that 2, 3, 3, there's only 2 sig figs. So we have to round this up to match the precision of this number, the 2 sig figs. And when you multiply or divide by an exact number, you multiply the uncertainty by that same exact number. So if you double this, you have to double your uncertainty. Lastly, we go about talking about percent difference. So if the accepted value lies within the range of uncertainty, then only random errors have occurred. However, if it does not, then random and systematic errors have occurred. And this is how you calculate the percent difference between the accepted value and your value. So accepted minus experimental over accepted, take the absolute value of that and multiply it by 100. So yeah, I think that's everything I need to cover. Thank you very much for watching.